Everyone knows that our exam one has been rescheduled to March 5th, that is next Thursday. Same time, just different week. Second thing is for today's classwork, since it's a remote class, it won't be a team assignment. Everyone has to submit their work individually. And also for grading purposes, what I've done is I've set it up as a quiz, not as an assignment. For today's class, what you need to do is everyone, once the class, when we have a few minutes left in class, you should go to quizzes, not to assignments, and there you'll see today's, where you can submit today's classwork, CW February 26th. And you click on that, and you'll see that there are 6 multiple choice questions that we'll go through in class, and everyone has to submit independently. That, and then a couple of other things that I wanted to show you on while we're on Brightspace. Problem sets. Problem set 3 was handed out in the last class, but I realized that there are some typos. So I fixed those and I uploaded a corrected copy on Brightspace. So you should refer to this copy today, and I'll also give you a printout when we meet on Tuesday. Also, one more thing, in the section Other Files module, you'll see the document list of formulas. And since now we have started chapter 3, I have added the formula for chapter 3 as well. And we might use a couple of them today. This is what we were doing last time. We started chapter 3, which is electric flux density, Gauss's law, and divergence. And we defined a new vector field called electric flux density. And this vector field is closely related to electric field intensity. Electric field intensity, as we know, it quantifies the strength of an electric field. It also provides the direction of the electric field. And for any field, any vector field, we can always visualize that field by drawing what we call flux lines corresponding to that field. So if we have a point charge, then the electric field will be radially away, outward from that point charge. And to visualize that field, we can draw arrows like that. And these are called flux lines of electric field intensity. And we know that for a point charge, electric field intensity is given by this formula. And here, right here, we see that there is this term permittivity, and this term is medium dependent. We've been talking about just free space so far. We haven't talked about any other material. But if we change the medium in which the charge is located, the electric field intensity is going to be different. So to remove the dependence on that medium, we defined another quantity closely related to electric field intensity, and that is what we call electric flux density. So if we multiply this electric field intensity by epsilon naught, then the epsilon naught in the denominator gets canceled, and we have a medium free vector field, which we call electric flux density. And this electric flux density can also be visualized by drawing its flux lines. We can draw arrows corresponding to the flux of electric flux density. And the flux lines of D, electric flux density, are more closely related to charge. So flux lines of electric flux density, they are more common in electromagnetics. And we also said that electric flux density is flux per unit area. It has this, since flux has the same unit as charge, the unit for electric flux density is coulomb per meter squared. Okay, so that's what we did in the last class. And today we'll continue here. So one very important law related to electromagnetics that we learned is Coulomb's law. And today we're going to learn another law, and that is called Gauss's law. And what this law says is that
the total flux leaving any closed surface is equal to the charge enclosed by the surface. And I'll explain what that means. So what we know is that electric flux density, D, is flux per unit area. So that means if we know the electric flux density and if we know a particular area, so let's say we have a surface area like this, and so we could write it as this surface area is, let's say, S. And in this, from this chapter, what we're going to do is we will consider vector surface area. So in chapter one, when we talked about surface, differential surfaces, and other surfaces, we talked about scalar surfaces. But from this chapter onward, we'll talk about vector surfaces. So we'll have a surface like this. Surface, an arrow, meaning it's a vector. And so if we, let's say, if we know the flux density and we know the surface as well, then we can evaluate the total flux passing through this surface. So we'll have, let's say, the electric flux density lines like that. And if we want to evaluate the total flux passing through that surface, so what we do is we do the dot product between D and differential surface, and we integrate that, and that will give us the total flux. Now let's look at this surface again. So in chapter one, when we talked about differential surfaces, we talked about, so in rectangular system, so in your, even in your formula sheet, you can see that in a rectangular system, there are three, maybe in the rectangular one, we didn't write it in the formula sheet, but this one is simple. In a rectangular system, the three differential surfaces are dy, dz, and then dz, dx, and dx, dy. And if we move to the cylindrical system, this one you will see in the formula sheet. So what we had was rho d phi dz, and then we had d rho dz and rho d phi. Similarly, in the spherical system, we have three differential surfaces, and these are all scalar surfaces. For the spherical one, we have r sine theta, dr. If we do dr d theta, then actually we don't need sine theta, we need just r. Then we have r sine theta and d phi, dr. And then if we do d phi and d theta, then we would get r square sine theta. So we have, for each system, we have three differential surfaces, and these are scalar surfaces. Now, in this chapter, we are going to make them vectors. That means we are also going to assign directions to them. So when we talk about in the rectangular system, the surface where y and z vary, but x is a constant. So it's easy to draw in the rectangular one. So let me do that. We can consider a cube or a rectangular parallelepiped is if the dimensions aren't equal. So when we say dy dz, so it could be this surface, the front of the cube, where y and z are varying, but x is fixed. And so now we assign a direction to that differential surface, and that surface is that direction is perpendicular to the surface. So in this case, the direction would be ax. Now we're going to put that direction over here. So dy dz has direction ax. Now, similarly, we can talk about the surface dz dx. That means y is fixed. So that would be this surface on the right. And the unit vector perpendicular to that surface would be ay. And now we're going to add that direction to the surface over here. We'll write ay. Similarly, the third one will have unit vector az. And we're going to do the same thing for the cylindrical system as well. In the cylindrical system, if rho is fixed and just phi and z vary, then the unit vector perpendicular to that surface would be a rho. In the second surface, we have d rho dz. That means phi is fixed. So the unit vector is a phi. And in the third case, rho and phi are changing, z is not changing, and the unit vector is az. We'll do the same thing to the spherical system surfaces as well. The first one has r and theta that change, and phi is not changing. In the second case, we have a theta. And the third case, we have ar. So these are vector differential surfaces that we'll be using in this chapter and other chapters. Any question up to this point? Now, for those of you who arrived late, one thing you might have missed is that for today's attendance as well as classwork, what you have to do is submit your classwork individually. So it's not a teamwork today. You can still collaborate with your friends, talk to your friends if you can, but everyone must submit their work to get credit, and that also counts as your attendance for today. All right, now that we know what a differential surface is, we can do this type of integral, right? So what this integral does is, basically what we're doing is taking the electric flux density and multiplying that by the total surface area. So multiplying flux per unit area by the total area gives us the total flux. So by evaluating this integral, using for ds one of these expressions, we can find the flux passing through any surface. And that is what we're going to do first. For this, we're going to look at problem, not this. So let's consider problem 4 from problem set 3. Where we're going to utilize the formula that we just learned. That means, so the one we're going to utilize is the total flux. We represent flux with the Greek letter psi, and flux equals passing through any surface equals d dot ds. Now, in this problem, what it's saying is that the electric field intensity in free space is given, and find the total charge enclosed in the surface in a given surface. So what we have here is an enclosed surface. The surface is bounded by 6 different planes. X equals 0, x equals 1, y varies from 0 to 2, z varies from 0 to 1. So first of all, what does this surface look like? So let me draw that. So in this surface, x varies from 0 to 1. So maybe I should move my axes. Oops. Maybe something like that. So we have a closed box, and what we want to do is electric field intensity in this free space is given. We know the exact expression, and what we want to find out is the total charge enclosed in this surface or inside this box. How much charge is stored in there if the electric field intensity is given by that expression, is what this question is asking. And now, what we learned is that Gauss's law, let's get back to it. What it says is that the total flux leaving any closed surface is equal to the charge enclosed by the surface. So if we are given this box, it is enclosing of certain volume, and the total charge enclosed will be equal to the flux leaving this box. That is what Gauss's law says. So it always involves a closed surface, some volume enclosed by surfaces. And the total charge within that volume is always equal to the flux leaving the surface. Now, here in this box, there are 6 different surfaces, right? There is the front. Okay. So we have 6 surfaces in this box. The first one, let's call that front. And if we want to find the flux coming out of the front, I'll need that later, so let me make a copy. Okay, so now what we're trying to consider here is, consider just the front surface, and there will be flux coming out of that surface, right? And we can evaluate that. Similarly, we can find the flux coming out of the top surface and the right surface and the left and the bottom and the back surface as well. So, and then we can combine the flux coming out of all the surfaces to get the total flux leaving the surface. And the total flux leaving this volume will be exactly equal to the charge enclosed by this volume. That is what Gauss's law says. So what we can do to solve this problem is find the flux coming out of each of the 6 surfaces first. And if we add them together, that should be equal to the total charge enclosed. Okay. That's the idea. Now, there are 6 different surfaces, so it will involve 6 different integrals. We'll consider the first front surface. And for the front, so we have to first figure out what the formula for ds is. In the front, x is fixed, y and z are changing. So the differential surface we need is the one that has dy and dz, and it has a direction associated with it, and that is ax. And if we're considering the front surface, remember the total x varies from 0 to 1. So in the front, x will be equal to 1. In the back, x will be equal to 0. Since we are talking about the front surface, we know that x has to be equal to 1 for this surface. Now we'll consider the formula, this formula. So we don't have the expression for D, but we have the expression for E. And we know that D equals epsilon naught times E. So what we can do is we can consider this given expression for E and multiply that by epsilon naught. When we do that, the epsilon naught in the denominator will cancel, and we'll just get the numerator part of that E as our expression for D. So let's just write that part. We get 2xy ax plus 3y square z square ay minus 4xyz az. That is our expression for just D. And what we have here is a dot product between this expression for D and ds. And ds is this. Okay, so now we know what a dot product is from chapter 1. So we multiply the ax components, we multiply the ay components and the az components separately, and we add them. And here, ds, the second vector, has only ax component, no ay or az. So the only term that survives is the ax components. So this will effectively be canceled. So what we get out of this integral is 2xy dy dz. And this is a surface integral. Surface integral means there are actually 2 integrals. It's a double integral. And y varies from 0 to 2, and z varies from 0 to 1. That's given. And if we see any x in this integrand, we know that x has to be exactly equal to 1. So this is 1. That means we're left with now just 2, and then we integrate y, we get y squared by 2. We integrate with respect to z, we get z, and we apply the limits. So the answer is 4. And the unit. So what we were given is that the unit for the electric field intensity, it's in millivolts per meter. So we have to multiply everything by 10 to the minus 3, or we can just say that this flux is equal to 4 millicoulomb. That's one surface. Now, any question about this part? That's the front surface. Now we'll similarly consider the back. So for the back, that means this surface. In this surface, y varies and z varies, x is fixed. We know that x equals 0, and now the unit normal vector coming out of that back surface, what would be that unit vector?
Negative AX.
Exactly. It would be negative AX, right? So that means for the back surface, ds would now be equal to, so dy dz part we already know, but you have to be careful about the direction. It's now negative AX. And now what we're trying to do is, so find the total flux coming out of the back surface. So we again consider this surface integral. What we have to do is d dot ds, and the process is now pretty similar. It's a double integral again, and we can actually copy a lot of things from before. So here, remember that we have to put a negative sign because AX is negative. And also, previously in the front surface, X was fixed at 1. Now here, X is fixed at 0. So this term goes away because we are doing the dot product with just AX component. This term also goes away for the same reason. And also on top of that, what we see here is that in this remaining expression, we have to set X equal to 0. If we set X equal to 0, the first term also becomes 0. So everything becomes 0. We are integrating 0. So that means our answer is also going to be 0. So the total flux coming out of the back surface happens to be actually 0. Next, we will consider the top. Top surface. Now, for this surface, we have z is given, and z is given as, let me see, 1. And what changes is x changes and y also changes. So the ds corresponding to this is dx dy a z. To find the flux from the top surface, we again do consider the integral d dot ds. It's a surface integral. And okay, we can copy, but we'll have to change it. These two terms are, now they won't cancel. Hold on. We have to change ds to dx dy az. Now we're doing dot product with a vector that has only a z component. There's no x or y component. So this term will become 0 and this term will become 0. And in the remaining term, wherever we see z, we have to set it equal to 1. So this z becomes 1. And this is also a double integral where x varies from 0 to, I have to check again, 0 to 1. And y varies from 0 to 2. And the remaining term is negative 4xy dx dy. So let's pull out that negative 4 and integrate with respect to x. We get x squared by 2. Integrate with respect to y, we get y squared by 2. X varies from 0 to 1. Y varies from 0 to 2. And we get negative 4. Negative 4 coulomb. So there are a total of 6 surfaces, and some of the surfaces I'm assigning as class of problems. So let me see which ones I'm assigning. Top and bottom. So you were supposed to do top and bottom, but I already did top. So let's look at left and right surface, and you can do the bottom surface. Okay, for the left, I lost the figure, so let me copy this. If we're talking about the left side, then what we know is that x does not, or no, sorry, y does not change. Y is fixed at 0. And the surface is ds equals dx dz ay, and there has to be a negative sign because we are pointing in, the surface is pointing in this direction, right? When we're leaving the surface, the flux goes in this direction. So negative ay if we're considering the left surface. And now again, we have to consider the surface integral of d dot ds. And x varies from 0 to 1. Z also varies from 0 to 1. And expression for d, we can copy from here. Then we need the expression for ds, which is negative dx dz ay. We'll put a negative sign in front of the integral. And now this time there is only ay component in ds. So what we know is that this will eventually be 0. This will also be canceled. So the only term that we have is we get 3y squared z squared dx dz. But we're considering the left surface where y is going to be 0. So the whole thing is going to be 0. That is the left surface. And since we did the left, we can easily do right as well, because the only difference is between the left and the right is the sign of this ds, right? If we're considering the right surface, we won't have this negative sign. We have a positive sign. So we can copy most of the things. We'll put a dot here, and then we have dx dz ay. We will remove this negative sign from the front. And this time, since we are considering the right surface, y is not equal to 0, but y has to be equal to 2. It is fixed at 2. And so now we can pull out the 3 as well as that 2. So we have 6. And then integral with respect to z and with respect to x, z square. Oh, sorry. Since we have actually y squared, that becomes a 4. And 4 times 3 is 12. So this becomes a 12. And then we have z squared dx dz. So integrating that, we get z cubed by 3. Z varies from 0 to 1. And then x varies from 0 to 1 again. So we get 12 by 3 equals 4 coulomb. That is the fifth surface. And now there is only one surface left. That surface is the bottom surface. And that is what I'd like you to try. And that becomes actually, I already set up the questions. So, so if you go to that quiz, so 2 I already did, but you can still answer it. Not 2. 3. 3 is the top surface, which I already did. And then 4 is the bottom surface. So right now you can try the bottom surface and find the answer to that. Just save your answer. Don't enter the answers yet. We'll do that at the end of the class. Just try to see what you get for the bottom surface. And I can go back up to where the question is so that you can see all the values.
So we should tell you the answer now or put it
If you got it, you can tell me.
a 0.
You got 0.
Yeah.
And while scrolling up, I also noticed that remember all the units have to be millicoulomb because the electric field was given in millivolts. So I believe I wrote just coulomb here. Let me fix that. Okay, for the top surface, it's not -4 coulomb, but it should be millicoulomb. For the left surface, we got 0. For the right surface, we got 4 millicoulomb. Let's fix that. And for the bottom surface, you got 0. Let's wait a couple of minutes to see if somebody gets a different answer or not. Anybody else got 0? Or something that is not 0?
That's what I got.
You got 0? Okay. So it should be 0. And now that we know how much flux is coming out of each of the 6 surfaces, we can also determine the total flux coming out of this box, right? That is, and now we'll change this notation in the integral. So the total flux, we'll write it as this. Total flux equals, so we will use this symbol, d dot ds. And this means closed integral. So what it signifies is that this is a closed surface integral. The previous 6 surfaces that we considered, they were all open surfaces, whereas this means a closed surface. And it consists of 6 surfaces: the front, top, back, up, down, left, right, all the 6 surfaces. So we take the sum of the 6 integrals. Okay, so we got 4, 0, minus 4, 0, 4, 0, minus 4, 0, 4 and then 0 again. So the total is 4 millicoulomb, right? So that is actually, I did, this is CW5 also. So you already have the answer for problem 3, 4, and 5. Now, so what we did in this problem was, all we were trying to do was the total charge enclosed in a volume. And the way we did that was by using the Gauss's law, which says that the total charge enclosed by any closed surface has to be equal to the total flux coming out of that volume. And that involves, doing several integrals, and which can be quite tedious. So there is an easier way to solve this problem, and that is through the use of something called divergence theorem. And that is what we're going to learn next. So what this theorem says is that, or what we're going to show is, this surface integral is closely related to a volume integral, which we can write as volume, and we'll find out what goes in here, a volume integral like that. And this might be easier to solve because this could involve sum of 6 different surfaces, or it could be more surfaces or less, but it involves multiple integrals. Whereas this volume integral, it could be just one integral. When we say a volume integral, it has dv, that means there is dx, dy, dz. So it's a triple integral, but still it's a volume integral, which might be much easier to solve. Now we'll look at this theorem called divergence theorem, which will relate these two integrals. And to understand this theorem, what we're going to do is consider a box again. So we already have a box, so let me copy that. So you know where the axes are, so I don't need to draw that. So let's say this is a differential volume. So it's a very small box. And it's total volume, we can say delta V equals delta X, delta Y, delta Z. So the length, height, and width of the box are delta X, delta Y, and delta Z respectively, and they are all differential lengths. And let's say the center of the box is the point P. And at P, electric flux density, it is known that it is equal to dx ax plus dy ay plus dz az. And to indicate that it is at point P, this value is at point P. So we'll use another subscript to indicate that. Let's say d naught, dx naught, dy naught, dz naught. And so we're going to derive the relationship between the surface integral and the volume integral. So it's okay if you don't copy this part because this is derivation. It's more important for you to understand the process. Now, so what we'll consider is the total flux coming out of the volume. And the process is very similar to what we did in that problem that we just solved. Okay, so we'll consider the front surface and the back surface first. Okay, so front plus back. And what we know is that if we're considering the front surface, the total surface area equals delta y, delta z, and the direction is ax. And for the back surface, we have negative delta y, delta z, and ax. And at the center of this box, we know the value expression for the electric flux density. It is given by this. And from the center of the box, which is, let's say, over here. Now, if we're coming to the front, from the center, if we're moving to the front, so what we have to do is we have to travel delta x by 2 in the ax direction, right? Because this total length is delta x and P is at the center. So if we move delta x by 2 towards in the ax direction, we get to the front surface, right? Similarly, to get to the back surface, we have to move negative delta x by 2 from point P. So now let's find the total flux coming out from the front surface and the back surface combined. For the front, we can write, or we don't need the integral because we are considering incremental surfaces. So we can directly write df, f means front, df dot the front surface area, which would be delta y, delta z, ax. And similarly, the flux density at the back, which we can denote as dB, times the surface area would be delta y, delta z, and then we need a negative ax. So let's just change that to negative sign, and we have this. Now, what are dF and dB? So all we know is the expression for the electric flux density right at the center, P. And what we are considering is a very small, it's a differential volume. So for dF, what we could do is we could use the expression for P, for D at P. So what we know is that at P, the expression is dx, it is given right by this, right? And whatever expression we have for df, we know that all that matters is the x component. The y component and the z component of this df are going to get removed because we are doing the dot product with something that has only ax component. So only the x component of df is relevant. So let's ignore the other components, y and z component. We're only interested in the x component. Now, what is the x component going to be? We can start with the expression at P. For P, it is dxo, but then we are moving forward in the ax direction. So what we could do is we can approximate the value for this component on the front surface. So we start with dxo, and then what we could do is consider the rate of change of dx. That means derivative, rate of change in the x direction times the step size that we're taking to get to the front surface. And that step size would be delta x by 2. Okay, so this is an approximation only, and it works because all the dimensions that we are considering, they are incremental. Similarly, now for the back surface, we can again start with the expression for dx at P. But then we are moving negative delta x by 2 to get to the back surface. So what we could consider is the rate of change with respect to x, and then step size is that we're taking is delta x by 2. Right? So those will be the expressions that we use. And remember, this is just the ax component. Similarly, this is also just the ax component. Ay and az components, they are not important, right? And then when we combine these, now we're doing the dot product with all that. So what we get is dxo delta y delta z plus derivative with respect to x, then delta x delta y delta z by 2. Okay, the ax dot ax is going to be 1. So this is for just the front part. And now what do we get for the other side, the negative part? So first of all, there is a negative sign. So let's write the negative sign. And then we have dxo delta y delta z. And then we get plus dx delta x y z divided by 2. So these two components come from the back surface. And now what we can see is that this will cancel that component. And then adding the remaining two terms, what we get is delta x, delta y, delta z, because this one has a half, this one has a half, and we can add those two to get this. So out of the 6 surfaces, we consider just the front and the back surfaces, and the total flux coming out of the front and back surfaces together is equal to this. Okay, delta derivative of dx with respect to x times delta x, delta y, delta z. Similarly, we could consider the left plus right. And very similar analysis will lead us to, for the left plus right, we'll get derivative of dy component with respect to y times delta x, delta y, delta z. And if we do the top plus bottom, we're going to get delta dz that. And if we combine the 6 surfaces together, we get the total flux coming out of this differential surface. And that we can write it as, so sum of all these, right? So this component, which is front plus back, then we have left plus right, and then we have top plus bottom component. And in all these components, we have delta x, delta y, delta z common, right? So, and also this we can write as delta v, the incremental, the differential volume. So we'll write it as delta v, and then we factor out that delta v component. So we get delta v, and what remains is derivative of dx with respect to x plus derivative of dy with respect to y, and finally derivative with respect to z. And then we bring that delta v to the left-hand side. Okay, so let me copy this. If we bring it to the left-hand side, it goes in the denominator, and then what we have in the right-hand side is this sum of derivatives. And then we are considering incremental volume. So what we'll do next is we will let that volume shrink to 0. So we are considering a very small infinitesimal volume. Now what we have ended up with here is okay, so on the left-hand side, what do we have here? remember in the numerator we have the total flux leaving a closed surface. And now we are doing per unit volume because we brought that volume to the left-hand side. Per unit volume, and we also added that limit. And so we have to say as the volume shrinks to 0. So all that is on the left-hand side, right? So the total flux leaving a closed surface per unit volume as the volume shrinks to 0 is equal to what we just found is this term. And this quantity, so what we have on the left-hand side, for any vector, we derive this for electric flux density D, but this is true for any vector. For any vector, this is called divergence of vector D. And notation, so how do we write that? Notation for divergence of D. So we'll use two notation in this class. So one is, we can just write div, divergence, D. Another will write del dot, this is dot product, D. Let me see what time it is. We have time. And that, again, in that notation, what is that del? So del is a vector derivative. Where del equals, so partial derivative with respect to x, ax direction. Then we have partial derivative with respect to y direction, and partial derivative with respect to z, az direction. Okay, so that is del. And then the other thing we have here is d. So we have del and we have d. So what is d? D is electric flux density in the rectangular coordinate system. It will have dx component, and then it will have dy component, and then it will have dz component. And what divergence of D means is the dot product between the del operator and the vector field of which divergence we are computing. So if we do del dot D, right, so we multiply the AX components, we get del by del X, partial derivative of dx, then we get partial derivative of dy, and then we get partial derivative of dz. And now what the divergence theorem is telling us is that the total flux leaving a closed surface per unit volume as the volume shrinks to 0 is given by divergence of D, right? So this is the total flux leaving the surface. And what we also know from the Gauss's law is that total flux leaving the closed surface is equal to the charge enclosed, right? So here, applying Gauss's law, so what we can say is that this is the charge, total charge enclosed, Q. So we can write this as the volume shrinks to 0, total charge per unit volume, charge per unit volume. And that is actually, we came across that term when we were talking about different types of charge distributions. Charge per unit volume, we call that volume charge distribution, and we denote that as rho V, and its unit is coulomb per meter cubed. Okay, so, all right, so what we have here is d dot ds divided by del V this is equal to rho V, and this is also equal to divergence of D. And the interesting thing about rho V is that this is volume charge distribution, right? So if we have the volume charge distribution for any region, to find the total charge enclosed in that volume, all we have to do is the volume integral of that charge distribution. So Q is given by the volume integral of rho V. The total charge enclosed is given by the volume integral of rho V, or in other words, since rho V equals divergence D dV. So this is the main formula today. So what we did was we related the total charge enclosed in a volume directly to the volume integral, and therefore we can bypass the surface integral, the closed surface integral, which would include several integrals. And we still have 10 minutes. Now, what we're going to do is so we saw the expression for divergence in the rectangular coordinate system. We did the derivation for the rectangular coordinate system. Now, if you look in the formula sheet, so you'll find that we have the formula for other coordinate system as well. So if we had done this derivation, starting with a differential volume in the cylindrical coordinate system or the spherical coordinate system, we would get the expression for divergence in the other coordinate systems as well. And in the other coordinate systems, the formula is it's a little more complicated. Any question?
I do have a question related to the exam. Is that the right time to ask later?
Sure.
So we have 1 hour and 15 minutes.
Mm-hmm. Yes.
And will you give us the equation sheet, or we just bring the same one that you gave it to us during lecture?
You should bring it yourself. I won't have a copy for everyone, so you should bring it, the one you have. And if you have lost it, then you can always download it from Brightspace. But you should have a paper copy because you're not allowed to use any electronic devices except for your calculator.
One equation sheet that you provided, not allowed to have anything more on that, right? Like
You
can
can
they go ahead.
you can write anything you want on it. That's okay.
Thank you.
But you're just bringing one sheet, right?
Right. Yep.
And if you do want to write more things on it, so it would be better to use the old sheet where there is only chapter 1 and chapter 2 formula, so that we have more space if you need more space.
Thank you.
Other questions?
I do have another question for the.
Yeah.
So, today that we want to find the total charge enclosed inside a cube or whatever, we have a different symbol, but we have the same unit at column. So C, what is the difference between that and Q? Charge.
It's the same thing. So the flux and charge, they are related things because the total flux coming out of a surface of
Yep.
out of a volume is equal to the charge. It's the same. They have the same dimension.
Well, but we cannot use Q, even though they have the same SI unit, but they're two different things. One on top of the, come out of the surface, the other one was in nature. So it's two different things. Is that correct?
Yeah, there are two different ideas. So in real life, there will be charge. There are no flux lines in real life. It's just something that we use to visualize vector field, its strength, and its direction.
Thank you.
Yeah. Okay, so other questions or comments?
Is the exam still only on chapters 1 and 2?
Yes, that won't change. That's correct.
When using capital E, that's for electric field intensity. When using capital D, is that also another electric field intensity field, or is that used for another? Because I know with magnets, there's like a bunch of them.
Can you repeat just the last sentence?
Like is capital D also used commonly for electric field intensity, or is the capital D field different than the capital E field usually?
They are different. They are different quantities. They are both vector fields, but they are closely related. So let me see if I showed that in the beginning. No. So it was in the previous lecture, right? So D is equal to epsilon naught times E. So they are both used to quantify the strength or the characterize an electric field. The difference is just the scaling factor, which is epsilon naught, which is a field dependent, medium dependent parameter.
Right, because you can Gauss's law. When I usually think about Gauss's law, I'm thinking about the Q enclosed divided by permittivity. So, but this is just a way of getting it into the E field beforehand, right? So that way it becomes equal to charge, right?
Yeah.
Okay, cool.
If we do all the analysis here, we can't use E directly here because you wouldn't be getting psi, but there would be an error of epsilon naught, right? So
right, and the units would be wrong, right?
Right.
Okay.
Okay, so hold on a second. You need to submit your classwork. So for that, we didn't manage to go through all. So there are 6 problems, as you can now go and see. The first problem is a true or false question that you can easily answer. For second problem is what we couldn't do, and so I'll give you the answer to that. It's 20 microcoulomb. Okay, so today what you need to do is go to that quiz. Okay, go to the quizzes on Brightspace, and there's only one quiz, so click on that. First question you should answer. You should be able to answer true or false. Second question, the answer is 20 microcoulomb. Third problem, so I solved it. 4, you solved it, and 5, it's just combining all the answers. And 6 is an easy question that you should all be able to answer if you are here, right? So you should, and everyone should submit that to get credit for today's class.